Hello everyone, my name is Varad Daoo and I am a doctoral student at the Department of Chemical Engineering, IIT Kanpur. So I welcome you all to this first lecture of states of matter, gaseous and liquids. Right? So in this class, what we are going to see is we are going to see the introduction to this chapter. Right? So let us start. Let me write this on the name of the chapter. So the chapter is Unit 5, and the name of the chapter is States of Matter. Right? Which are liquid and gases. So first, in the first sub part of this chapter, we are going to study about gases, and in further, we are going to study about the liquid. So this is lecture one, right? So let us start. So in the previous units, what we have learned about the properties related to single particle of matter, such as an atom or a molecule. However, most of the observable properties of a material are bulk properties, which are associated with the collection of large number of individual particles. Right? These are very important because we can actually see this and help us understand how the world works. Right? For example, an individual molecule of liquid does not boil, but the bulk of the liquid boils. Right? The individual water molecules do not wet water, but water, which represents a collection of water molecules, has wetting properties. Right? So this is what we should be writing now. Right? So this is lecture one. Right? So what we have done is an individual molecule of a liquid does not boil. So this is the introduction part, right? So let us write this down. Introduction does not boil, but the bulk of the liquid boils, right? Similarly, what we can say is the individual water molecules, the individual molecules do not wet, but water which represents, but water, right, which represents a collection of water molecules has wetting properties, right? We speak of different forms of water such as ice, which is the solid form of water, liquid water, and steam, which is the gaseous form of water. In all these three states of matter, chemical composition is same, right? Which is pure H2O. But the physical properties of ice, water, and steam are very different, right? The characteristics of these three states of matter depend not only on the energies of the molecule, but also on the manner in which the individual particles binds or aggregates to form the bulk material, right? Therefore, it is necessary for a chemist to know the physical laws which govern the behavior of matter in different states, right? We should write this down. So, the characteristics of three states of matter. The characteristics of three states of matter. The characteristics of three states of matter depend not only on the depend not only on the energies of molecule, but also on the manner in which the individual particles bind or aggregate. Individual molecules bind or aggregate to form bulk materials, right? Similarly, therefore, it is necessary for everyone for us to know the physical laws which govern the behavior of matter in different states. Behavior of matter in different states, right? So this is the motivation which we have. So in the present unit, we will learn about how the bulk properties of material arise from the behavior of individual particles, which are atoms, ions, or molecules. We shall also learn more about the different physical states of matter, particularly gases and liquid, right? So in present unit, we will learn about the bulk properties of materials arising from the behavior of individual particles, right? We shall also see more about the different physical states of matter, particularly gaseous and liquid state. So as we all know, there are three states of matter, right, which are solid state, liquid state, and gaseous state, right? So matter exists in three different physical states, namely solid, liquid, and gaseous state. The important characteristic of these states are, right? So let us start. So states of matter. Mostly we say the states of matter are three types, right? So these are, first is solid state, right? Second is liquid state. The third is gaseous state, right? So solid state, a solid possesses a definite volume and a definite shape, and the shape of the solid can be changed, but it usually requires considerable force, right? Therefore, solids are generally hard and rigid, right? Some common examples of solid are like iron, silver, common salt, etc. Right? So let us write this down. So what is a solid state? Right? So a solid possesses a definite volume, right, and a definite shape, right, and the shape of solid can be changed, but it usually requires considerable force, right? Therefore, solids are generally hard and rigid. Solids are generally hard and rigid. So examples could be iron or silver, common salt, right? Second would be the liquid state, right? Liquid state. So a liquid possesses a definite volume but not definite shape. Right? It takes up the shape of the container in which it is placed. Liquid also has a tendency to flow. For example, water, alcohol, milk. Right? So a liquid possesses a definite volume but not definite shape. Right? It takes up the shape of the container in which it is placed. Right? Liquid also has a tendency to flow. Has a tendency to flow. The example could be water, alcohol, or milk. The third step is the gaseous state, which we are going to study in detail. So a gas neither possesses a definite volume nor the definite shape. A gas occupies the whole of the volume of the vessel in which it is placed. Right? It also takes up the shape of the container. For example, air, carbon dioxide, water, or hydrogen. Right? However, it may be noted that a substance may exist in any of the three states under appropriate conditions of temperature and pressure. This is very important. Like this what basically what says the water can exist in solid phase as well as in liquid phase as well as in vapor phase. It can exist in all three phases provided that the temperature and pressure are like that. As well, all know water, like, right. So in general, a substance is said to be a solid if its melting point is above room temperature and under atmospheric pressure. Liquid if its melting point is below room temperature and boiling point is above atmospheric temperature, right? And a gas if its boiling point is below room temperature under atmospheric condition, right? It may be noted that a given substance may also exist simultaneously in all the three states under specific conditions of temperature and pressure, right? For example, water exists in all three phases simultaneously at a particular pressure and temperature, and the temperature at which all three phases exist simultaneously is also called as a triple point, right? So let us write this down. So a gas neither possesses a definite volume nor definite shape. Gas occupies the whole volume of the vessel in which it is placed. Okay? It also takes up the shape of the container. Okay? So example could be air, oxygen, carbon dioxide, okay, etc. Right? However, it may be noted, just like this. However, it may be noted that a substance may exist in any of the three states under appropriate conditions of temperature and pressure. E.g., for example, water can exist in all three phases at different predefined. So this is very important conditions of pressure and temperature. Like for example, at 298 Kelvin and 1 atmosphere, we know that the water exists in liquid phase, right? However, if the temperature is changed to 100 degrees centigrade, we know that water will evaporate and will get converted into gaseous state. Right? So in general, what we can say is, in general, a solid, a substance is said to be, right? In general, a substance is said to be a solid if its melting point is above room temperature under atmospheric pressure. Atmospheric, right? This could be like solid if it is said to be a liquid if it is said to be a liquid if its melting point is below room temperature, and boiling point is above room temperature. And it is said to be a gas if the boiling point is below room temperature under atmospheric pressure. Under atmospheric pressure, right? So now let us define what is triple point. So let me go on to the next page, right? So the temperature at which all three phases exist simultaneously is called triple point, right? Right? Like for example, water exists in all three phases simultaneously is very important. Simultaneously at 0.01 degree centigrade and 4.58 millimeter of Hg pressure, right? So we'll study about this unit of this pressure, millimeter of Hg, in future classes. It's just that it is important for you to remember this, right? To know this. So what we are saying, In addition to this, scientists have also figured out two more states of matter, which are the plasma and Bose-Einstein condensation. However, these are not the phases which we study at this level of course, right? So it is beyond the scope of this syllabus to study about them, but it is also useful for you to know that in reality there are five states, which includes the plasma and Bose-Einstein condensation as well, right? To understand the behavior of various states of matter, scientists had been trying to understand the constituents of matter, right? So in the present unit, we shall explain some of the important general characteristics in terms of elementary constituting particles, right? So let us try to understand what is the intermolecular forces, or what are the various types of forces which are present inside this, right? So the next section is intermolecular forces, right? Intermolecular forces. So these intermolecular forces, right? These are weak sort of a process, and there are various kinds of sub forces into this, right? So the forces of attraction and repulsion between the interacting particles are called as intermolecular forces, right? So let us write this down first. So the forces of attraction and repulsion between interacting particles are called as interacting particles, right? Are called as intermolecular forces, right? So such forces exist in all states of matter and are responsible for many structural features and physical properties of matter. It may be noted that this term does not include the electrostatic forces that exist between the two oppositely charged ions, right? And the forces that hold together the atoms or molecules together, right? So let this also write this down. Such forces exist in all states of matter, in all states of matter, and are responsible for many structural features and physical properties of matter, right? And these forces do not include electrostatic forces, right? Forces between two oppositely charged particles. So the first intermolecular forces which we are going to study about are the intermolecular forces are weak forces, right? Let us write this down. So the intermolecular forces are weak forces, right? And there are various types of these forces, right? So these are present even in case of non-polar molecules such as hydrogen, oxygen, chlorine, and CH4 in a solid and liquid state. It has been observed that even non-polar substances such as hydrogen, chlorine, and methane can be liquefied, right? And we all know that noble gases are monoatomic and their atoms do not combine to form molecules because they have stable field electronic configuration. But these gases can also be liquefied. This means that some forces must be operating at the liquid stage, right? And these forces are, however, very weak as indicated by their low melting and boiling points, right? The existence of weak attractive intermolecular forces was first proposed by Dutch scientist van der Waals, who studied the effect of these molecular forces on the behavior of real gases, right? So in his honor, these forces are also called as van der Waals forces. And such forces came into existence due to the interplay of positive and negative charges between the neighboring atoms of non-polar molecules when they are very close to each other. And the intermolecular forces arises due to there are many various reasons because of which it arises. These are dispersion forces or London forces, or dipole forces, or dipole induced dipole forces, or hydrogen bonding, right? So we are going to study in detail about it, but before that, let us write this down, right? So these forces, right? So the existence of weak intermolecular forces was first suggested by Dutch scientist Johannes van der Waals, who studied the effect of these molecular forces on the behavior of real gases, right? And in his honor, these forces are also called as van der Waals forces, right? So in this chapter, we are going to study this term van der Waals forces is going to come very often, and van der Waals forces are responsible for the liquefaction of gases, right? Are responsible for liquefaction, right? So such forces came into existence due to the interplay of, which is very important. So such forces, that is the van der Waals forces, came into existence due to the interplay of the positive and negative charges between the neighboring atoms of non-polar molecules when they are very close to each other. And these arises because of the following interactions, right? So these are due to the either one of the following: dispersion forces, also called as London forces, or dipole-dipole interaction, or dipole-induced dipole, or hydrogen bonding. So for we are going to study about the first force, which is dipole forces, right? Dispersion forces, or London forces, right? Right. So atoms and non-polar molecules are electrically symmetrical, and have no dipole moment because of their electronic charge cloud is symmetrically distributed. But the intermolecular forces may exist even in these non-polar molecules, such as noble gases, right, or non-polar molecules like hydrogen, nitrogen, and oxygen, etc. This is because the noble gases and non-polar molecules can be liquefied, suggesting that there must be some intermolecular attraction. In other words, a dipole may develop momentarily even in such atoms or molecules. In order to understand these forces, right, let us consider this figure. Let us consider that we have a circle. Right? These are the two noble gases, right? Let us consider this. This is the nucleus, right, of that molecule. This is the nucleus. Let us assume that this is nucleus, positive charge, and this is atom A, and this is atom B, right? So what we have is, in this case, what we have is symmetrical distribution of electronic charge cloud, right? So in other case, where we have a dipole, let us see, these are the dipoles, right? So in this case, what is going to happen? The arrangement would be like this. So nucleus would be like this. Here we will be having a delta charge, delta plus charge, delta minus charge, delta plus charge, and delta minus charge, right? And this is going to be atom A, this is going to be atom B, and this is nothing but instantaneous dipole, right? This is going to be, let me write this down, this is induced dipole, right? And this is instantaneous dipole. So what we have is, we have more electron density on the right hand side. Because of this, what is going to happen is, there are going to be forces of attraction between these two. These are what? Forces of attraction. And this full figure represents the, so let us box this figure, right? Yes. And this whole figure is going to be called as origin of instantaneous dipole. Instantaneous dipole. So both of them are instantaneous dipole. These are nothing but dispersion forces or London forces. So dispersion forces and London forces are nothing but induced dipole, right? Instantaneous dipole, right? So in order to understand the origin of these forces, let us consider two noble gas atoms, right? So these are the two noble gas atoms, atom A and atom B, very close to each other. Each atom is uncharged because its electron charge is symmetrical, right? So this is the electron charge which is symmetrical, right? Just figure this. However, due to the motion of the electrons, we can imagine that for a fraction of time, the electron charge distribution in one of the atoms, let's say atom A, becomes unsymmetrical, right? That means it's like this. That is, this is right. That is, charge cloud is more on one side than other, right? During this very short time, the unsymmetrical centers of positive and negative charges do not coincide, right? So here we have more positive charge. Here it will be more negative charge. As a result of instantaneous distribution of electrons in this atom, there is a small temporary dipole known as instantaneous dipole, right? So we can write this, right? Small instantaneous dipole is nothing but temporary, right? This small temporary is nothing but instantaneous, right? This instantaneous or transient dipole distorts the distorts the electronic configuration in the neighboring atom B, right? Because of the dipole generated here, it distorts here, right? And induces dipole known as instantaneously induced dipole, right? So this is going to be, oh, let me use different color. So this is going to be, as you can see here, what we have in it, this is going to be instantaneous dipole, and because of this instantaneous dipole, we have induced dipole, right? The temporary dipoles of atom A and atom B attract each other, and these attractive forces are called as instantaneous dipole and instantaneous induced dipole forces, right? So let us write this down. Let's write it down here, right? The attractive forces, right? The attractive forces between instantaneous dipole and induced dipole are called as dipole forces, right? Similarly, temporary dipoles are induced in non-polar molecules also. And these forces of attraction were first studied by German scientist London, and hence these are called as London forces, and are also called as dispersion forces, right? So these are also called as London forces or dispersion forces, right? So these forces are always attractive, and the interaction energy due to these forces is proportional to the 6th power of the distance between the molecules, right? So what we can do is dispersion or London forces are proportional to 1 to the power r to the power 6, where r is the distance between the molecules. And these are always attractive, right? And these are significant only at short distances, right? Significant only at short distances, which are approximately 500 picometers, right? And these also depend upon the polarizability of atom or molecule. Now, what is it depends on polarizability of atom, right? Now, the question arises: what is polarizability? The polarizability of an atom or a molecule is a measure of the ease with which the electrons and nuclei can be displaced from their average position. The more easily the electrons and nuclei can be displaced, the greater the polarizability. The larger the polarizability, the greater is the magnitude of the instantaneous dipole, and hence stronger are the London forces, right? So the polarizability, right, visibility of an atom or a molecule is the measure of the ease with which the electrons and nuclei can be displaced from their average position. These forces are responsible for condensation of noble gases, right? However, these forces are very weak forces, and the strength of these forces depend on the strength of London forces depends on various factors, out of which one is size of the molecule, second is the number of electrons present in the molecules, okay? And the third is molecular structure. For example, large molecules have much diffuse charge clouds, hence there are greater chances of its distortion. Therefore, the strength of molecular forces strength of van der Waals forces increases with increasing molecular size. So, the strength of van der Waals or London forces increases with increasing molecular size. Increases with molecular sizes, right? Moreover, the larger number of electrons in the molecule, also the larger the number of electrons in the molecule, the greater is the chances of distortion of electron clouds, right? This is number one. This is number two. The larger the number of electrons in the molecules, the greater is the chances of distortion of electron clouds, right? Distortion of electron cloud. The shape of the molecules also has a significant effect on the magnitude of London forces, right? The branching chain makes the molecule more compact and therefore decreases the surface area. Therefore, the overall attraction between the molecules, which depend upon the surface area, becomes less, and hence boiling point increases with branching, right? This is also very important. The branching of the chains makes the molecule more compact and thereby decreases surface area. Therefore, the overall attraction between the molecules, which depend upon the surface area, becomes less, and hence boiling point decreases with branching. Right. So in this class, let us now do the summary. In this class, what we have seen that there are three states of matter, which are nothing but solid, liquid, and gases. We have defined three states of matter as well. Defined the states of matter. We also studied about triple point. What is triple point? Then we studied about the different type of forces which exist between the molecules, right? Intermolecular forces, right? Intermolecular forces. And in intermolecular forces, we saw that there are four types of forces, and we have studied about the first type, which is nothing but van der Waals or London forces, right? London forces, right? So in the next class, what we are going to study, we are going to study about the other three forces, right? Which are dipole forces, and dipole induced dipole forces, and the fourth one, which is hydrogen bond, right? Hydrogen bond forces, right? So thank you all for attending this class, and I hope to see you again in the next class. Thank you.